Howdy, folks. Last talk of the day. This is Dave Hulton. If you don't know who Dave Hulton is, you've been living under a rock, particularly down here in Southern California. He's the organizer of TorCon down in San Diego, also TorCon Seattle, and soon to be TorCamp. So if you've ever wanted to go to the Germans' Chaos Computer Club summer camp but couldn't afford the trip to Europe, it's going to be kind of like that, but local. Well, local for me and him, but not for you guys. Yeah, not nearly as many German backpackers. So Dave is going to be giving a newer version of the GSM hacking talk that he gave not too terribly long ago, which, if you guys haven't had a chance to check it out yet, I totally recommend paying close attention to this one. It's pretty freaking cool. We'll go ahead and let you get started and check it out.
Yeah, thanks a lot, Noid. All right, so just to give you a brief intro about myself, I'm going to try and cover all of the different things that Strom mentioned in his talk earlier. Actually, while he was giving his talk, I was looking through my slides and going like, oh shit, I got to remove this and like move things around and got to make sure I do a real intro. And so here's my real intro. My name is David Hulton. Obviously, you've already heard an intro. Oh, hey back there. How's it going, Queeg? So, I'm like the chairman for TorCon. I also do a lot of stuff with FPGAs, if you guys know what that is. And mostly, specifically, crypto cracking with FPGAs. One of the interesting projects that we've been working on recently is using FPGAs to crack GSM. So, first of all, there's a few things I'm going to cover, and before I even cover this stuff, who knows what GSM is? Anyway, yeah. Who uses GSM? Who uses something that isn't GSM, like CDMA? Sprint? Okay, cool. So I'm going to show you a little bit about how GSM works. I actually I didn't do any of the protocol stuff, so I just kind of have a high-level view of this stuff. But I did do all the cracking A5 stuff. So any questions on that, feel free to hammer me with them. And I'm going to show you some of the different projects we've been working on for actually receiving GSM signals. So first of all, GSM is widely deployed. AT&T, T-Mobile, pretty much like almost all the carriers in the world use it, aside from a couple carriers here and a couple carriers in India that use CDMA. And so it's really a hugely widely deployed system out there. And they use a couple of standard sets of algorithms for doing their authentication and their encryption, namely A3, A8 for authentication, and A5 for encryption. I'm going to cover that a bit more in just a little bit. So here's a big graph which Strom would probably say is inappropriate for a talk like this. But really all you need to focus on is that there's this huge infrastructure here on this side, and here's your cell phone, here's these towers, and then basically it kind of goes back and routes out to, like to be able to call people and stuff like that. And we really only focus on this portion right here, because we don't really have easy access to all this stuff back here, aside from breaking into a telco or something like that. So, so we're going to focus on this. What's that? So, you guys know what a BTS looks like? Yeah. This is an example. Yeah. So this is an example. There are also BTSs that look like this. Yeah. They don't actually grow like normal trees, but there are some striking similarities between the two, I guess. So yeah, they have deployed some of these. It may be a little tricky. You get full bars on your cell phone, and you look around and try to see where the base station is, and they could be hiding right behind you. You never know. So in summary, GSM is old. It's been around for decades. GSM is big. It's like the most widely deployed cell phone standard out there, and there's base stations all over the place. I think that there's over 2 million subscribers, which makes it comparable to like the internet, in size of devices and the network. And And really, like, up until this point, we haven't actually been able to, start talking to these devices. Before we had all these ways, we can create sockets, we can do port scans of, systems and stuff like that. But until now, it's been very obscure, like, how to actually talk to a cell phone. All that stuff has been really closed, and people don't really know how to do that stuff. So we wanted to look into this and see, like what's going on this huge network. So a couple of the devices that we've been looking at, we use the Nokia 3310, which is actually a really cheap phone. You can find these on eBay for like $5. I think that Steve, the other guy I give this presentation with, bought his for $1 and paid like $6 for shipping or something like that. So they're very cheap. You just get a debug cable, you hook it up to your PC, and you can, we have software on our website where you can just start watching your own traffic. So you can see all the packets that get sent to and from your phone. So that's really useful for our debugging purposes. And it's just a really cheap way to start looking at the stuff. If you actually want to see other people's traffic, we've been working with the USRP, the GNU Radio project. Have you guys heard of that before? Yeah, so it's a software-defined radio. You buy a system that looks like this over here. And it costs you about, I think they're about $600 right now. You can get a front end for it and stuff like that. In total, it maybe costs you about $900 for a decent antenna and full setup. And you load our software on there, and you can basically just start, doing whatever sort of software-defined radio stuff you want to do. And so I'll go into the project a little bit more in the next slide. But there's also a couple other different ways of intercepting GSM traffic. There's these OMAP development kits, which is basically the development kits that people use for like developing their actual cell phones. And so you can put these into debug mode. You can have it forward you the packets. There's all sorts of cool debugging things you can do with those. And I believe that those currently cost about $10,000. They're a little bit expensive. And then on the really high end of things, there's commercial interceptors that like law enforcement and other people use. And these can cost a lot of money. I'll go into that in a little bit. So talking about the GNU Radio project, the support mostly works. It's actually, I would have demoed it here, but we've been having some trouble with going through airports with our GNU radios. Steve, my co-presenter, actually got stopped in the UK when he was traveling to a conference in Dubai to demo the stuff. And basically the customs like confiscated his GNU radio and his cell phone. And they were kind and gave it back to him after he got back to the UK, but it's kind of, we're just a little paranoid about this stuff now. But if you have a USRP, you can download the software and you can check out all this stuff. Essentially, the software lets you run Wireshark on GSM. So you tune in the channel. It creates basically a fake network device. You fire up Wireshark on the network device, and you can see all the GSM packets going on. Right now, it only supports the slow association channel, but this still means that you can see like all the cell phones that are connected to the base station sending out their broadcasts and stuff like that. You can't actually see calls, but you can see people associating. You can also do like location tracking. If you know somebody's ID on the network, you can see like how close they are to different base stations. There's lots of different things you can do with this. In order to do other more advanced things like actually monitoring calls and SMSs, there's a couple of things we've been working on. We're trying to implement Viterbi error correction stuff, and we've got it mostly working, but we haven't gotten it working in real time yet. So there's a lot of optimization that needs to be done with that. Then there's also this thing with channel hopping that we found out that GSM has this optional channel hopping thing that they do, where when you place a call, they will, for every frame, they will hop to a different channel. And so this is really difficult because now we have to start messing around with the USRP firmware and setting it to follow that hopping sequence in order to capture everything. So that's definitely possible with the hardware, but it requires some time to get all that stuff to work. And then, of course, there's encryption that secures this whole thing, so we have to get around that. And that's mostly what I'm going to be focusing on later on this talk. But with the first few points here, we're looking for help. If anybody here is interested in working on RF stuff, check out our website, send us an email. We're looking for people to help out with optimizations and things like that. So here's some examples of some frames that we've actually seen from the USRP, and you can also get these from the 3310, the really cheap cell phone. This is spit out from a program you can download from our website. This is really interesting right here because this is actually your subscriber identifier in the network, which according to the spec is never supposed to be sent over the network in plain text, because this is basically your user ID in the system. So if I know this number, I know, like exactly where you are on the network. And so if I was trying to track, like where are you right now, I could just, look for your IMSI on the network and then triangulate where you are based on the base stations and stuff. And so there's a lot of interesting implications for this. They actually do create a temporary identifier on the network, which they're supposed to use, but this is a really interesting thing that we found out with the whole system, which makes it seem like people could be easily tracking other people without even having to break encryption. And then there's also these bits that tell you which algorithms are actually available on the network when you authenticate. And this is also interesting because with this you can see that like the base station advertises what algorithms it supports, and then you can also advertise what algorithms you support. So this is kind of how the man-in-the-middle attacks work. You can set up a fake base station. Somebody connects to your fake base station. You negotiate them down to no encryption, and so there's all sorts of different ways to exploit stuff like that. Assuming you have like oh, go ahead. What's that?
Is viewing this kind of information legal?
I'm not entirely sure. Oh, sorry. Thanks, Strom. The question was, is viewing this data entirely legal? And my answer was, I'm not entirely sure. So, what's that? Yeah, I mean, listening on this frequency is kind of technically illegal. Yeah, but I mean, it's also iffy if you have a debug cable hooked up to your phone and you're just watching your own, stuff coming off of your phone. It isn't like you have your own scanner that's listening on the frequency. So, I don't know how you want to interpret the laws with that, but yeah. So what now? Various hardware will definitely capture traffic, and it turns out that some base stations we've seen actually send SMSs unencrypted. This is a very weird thing that we saw with some base stations up in Seattle. We're not sure how much this applies to like other networks and stuff. But what do we do about capturing real conversations? It turns out that some countries don't actually use any encryption at all. And some of them use this weaker standard called A52, which is mostly given to like the kind of unstable countries that we want to watch after. Most of the real countries, get A51. Not implying that we're a real country or anything, but like for example, the U.S. uses A51. And so that's really kind of like the holy grail of the whole thing. That's really what we want to go after because that's what most of the people use, and that's really the interesting, difficult one to attack. So looking at our security here, there isn't really any security on the internal network. Like you can plug in and start just like sniffing any traffic and stuff. But of course, we don't want to break into the service provider. So we've already established that there isn't really any security on that side. So that leaves, well, obviously there's security over the air. But this is POEM, so there isn't really any security at all on GSM anymore, which I'll cover in a little bit. So for commercial interception, there's lots of different options that are very expensive that are available. You can actually go just search for like GSM interception on Google, and you'll see a bunch of interesting devices pop up. They range. We've contacted some of these places, and they range from like $70,000 to $500,000, depending on how many channels you want to listen to at a time, et cetera. And this is with active equipment that'll actually create a fake base station, perform a man-in-the-middle attack on A51, and then let you listen to stuff. But all of these are unreliable. You have to be really close to the target. Like I think it's within about 100 meters or 300 meters or something like that. because you actually have to have a signal that will overpower the other base stations in the area and make them connect to you, and then you forward their traffic along. And so, there's stuff out there that will currently do this, but it's kind of inconvenient. What we were really aiming for is a passive attack, and there's actually stuff out there that currently exists for about $1 million, which is really expensive, obviously. And but with passive equipment, you know, like right now, I can be up to 20 miles away from a base station and have, you know, like a cell phone conversation if it's line of sight. With passive equipment, you know, somebody can be anywhere within the range of the base station and your cell phone and be able to pick up all of your stuff. And so, you know, like I could just be sitting at home on my couch, you know, listening to someone's conversation on the other side of the city. And so we really wanted to do the lazy attack, you know, and be able to just like lounge around instead of having to chase after people and stuff. So yeah, there's 3 algorithms, A50, A52, and A51, and all of these were actually reverse engineered and broken back in 1998. And they actually, a lot of the attacks on them were actually published before they were even leaked. Like, they started figuring out some things, and then people started writing all these papers on like ways to break it, and then eventually they actually found out, you know, what the algorithms were, and then, you know, even more papers came out on like flaws in it and stuff. So all of these papers about it being broken were mostly academic. They didn't really apply to like the real world. If you know exactly all of the audio that's going across the conversation for, you know, like 3 minutes, then you could crack it in like, you know, a couple months, you know, and stuff like that. So it's kind of stupid stuff like that. But this is all in 1998, and so now that it's you know, 10 years in the future, we can do way better, and I'm going to cover that in a little bit. So a lot of these algorithms are proprietary, and so they had to be reverse engineered. And as I mentioned before, like, without breaking any encryption at all, you can still, you know, track people and all that sort of stuff just because all this information is leaked. And initially, the key was actually artificially weakened. They set the last 10 bits of the key to zeros, and then after we reverse engineered and found that out, then they're like, oh, okay, our bad, you know, we'll fix that, we'll throw all the key bits in there. And but it just seems like there's lots of little things involved in the whole process that make it, you know, really fishy. Like, so anyway, there are lots of key recovery systems available for A52. A51, there are very few that can actually do it passively. Another interesting thing that we've been starting to work on with the, if you check out the THC wiki, is SIM Toolkit. How many people have got their SIM in the last, like, say, 3 years? Like, yeah, a lot of people here. So all of you have pretty new SIMs, like 32K or 64K or something like that. A lot of these SIMs actually have a Java virtual machine running on them, and if you actually check out the specification, the operator, like T-Mobile or Singular or whatever, can actually send silent updates to your SIM card and execute whatever code that they want. And there's a full API for this stuff that's very interesting, like call control, binary updates. You can, one thing that we found is that you could actually upload a program to it where whenever you make a phone call, it also calls another number and forwards your conversation to that. And so there's all sorts of interesting interception things that can actually be done, you know, just on the software that runs on your SIM card. So we're starting to develop for the SIM cards and trying to see what sort of things happen with that. But very interesting stuff, and it's just kind of cool that you have, you know, a little computer inside of your SIM card. So anyway, summary about the security is that really there isn't any real security. There's a lot of, you know, kind of, well, we consider snake oil in the whole thing, but yeah, basically there isn't really any. So to go over cracking A51, we have a cell phone, like one of these, and a base station. And on your SIM card, there's this thing called the KI, which is your actual like master key that is a symmetric key between your cell phone and the base station. And so for authentication, you run that through A8, which is our authentication algorithm. It generates random numbers, does an exchange, a verification, but essentially it drops out a session key, which is your KC value. This then gets fed on to A5, which is actually a stream cipher that uses your session key for encrypting your whole conversation and stuff. And then you carry on your conversation over the phone and stuff. So this all works like a standard stream cipher. Are people familiar with crypto or stream ciphers in here? Okay, all right. The general idea is that has anybody here ran like rand or random, functions like to create random numbers? Yeah. Okay, so like before you run a random function, you obviously seed your random number generator, and some people do it with time or whatever. And so assuming that you seed your random function with the same seed, you'll end up with the same stream of random numbers coming out of your random number generator. So if you think of A5 as just a random number generator, if you feed the same key, and there's also initialization vector, basically the same key on both sides, it'll emit the same random stream of sequences on both sides. And so then you just do a simple XOR with your plaintext. That encrypts it. You send it across, and then XOR it with the same exact stream on the other side, because you can reconstruct it with the same key. And then you end up with your plaintext on the other side. Well, this is all done like on the fly. It's bit by bit. It's all shift registers and stuff. And so basically the full frame is 114 bits, but it's all kind of done in line with everything. So and then you create a new frame number and like send a new frame number. So there's essentially a unique frame number for each frame that you're sending across, which is 114 bits. So looking at A51, it's actually a set of shift registers. And anybody here know what a shift register is? Yeah. Okay, cool. So the general idea with a shift register is that you have an array of bits. So all of these are filled with bits. And just looking at like this one register here, with this you can have like bits inside of there, and then when you clock it, basically all the bits get shifted to one direction, and then obviously like this bit is going to get shifted off to that side, and nothing's going to get shifted onto this side. And so what you end up shifting into this side is the XOR of these bits here. So so basically this bit here will become dependent on the bits that were here before. And so it's kind of a way of applying XOR to a bunch of bits recursively. People use it a lot for different error correcting codes. People do like encryption ciphers. There's lots of different applications for shift registers, but that's kind of another talk. Anyway, so they decided to use 3 shift registers, and they kind of set up this clocking way of making it so you can only really clock it forward, which is actually a very weak way that they implemented it. And so the general idea is that you take your key, like your session key, and you take like the first bit of it, and you shift it into these bits over here. So if the first bit is 0, you drop a 0 into there, a 0 into there, a 0 into there. And then for the next bit, you clock this, so this gets shifted into there, that one gets shifted into there, and so on. And you put the next bit in. And so you repeat this process, so all of the bits of the key get shifted in. And as these bits start hitting these tap registers here, they get XORed with all these other ones, and then get XORed with your input here. And so things just start getting mixed around inside the registers. And then you clock in the frame number, you clock it for like 100 clock cycles. But essentially, this is kind of seeded with your key and your frame number, and then it just starts emitting random bits out the other side. So then for actual output, these bits get XORed together and sent out, and that's what actually gets XORed with your plaintext or XORed with your ciphertext to decrypt it. Does that make sense at all, or should I go with that? If you know, okay, all right. So when we were originally planning this whole attack and trying to figure out a way to do this, all these other attacks weren't really practical. There's no way that we're going to be able to guess exactly all the audio that happens for 3 minutes or 2 minutes. And we definitely don't want this to take like months to crack a single conversation, So it turns out that we found some known plain text in like the first few frames. And so this means that we can do this entirely fully passively. And we used a combination of basically a rainbow table attack and a couple other methods to make this all work. So one thing that we did is that we have these frames that are 114 bits long. And we take it and we take 64 bits at a time at different offsets inside there. And we use these as kind of like vectors for our thing. It'll make more sense in just a second here. But essentially, we have 64-bit values, and we have 204 of them for all of the known plaintext that we have. And how this is useful is that if you kind of think of A51 as like a rainbow table, you know, like with landman rainbow tables, if you guys are familiar with those, you have a mapping of a password to a hash. And the idea with hashing functions is that you can't go back from the hash to the password. I mean, that's why you store the hash on the hard drive. You know, so if somebody grabs that, they can't really figure out what your real password is. So rainbow tables are great for stuff like this. You just create you know, this mapping of passwords to hashes, and then later on you can look up the hash inside the table. And there's all sorts of optimizations that I won't go into with it, with how like to compress the tables and all this kind of stuff. But essentially, we can treat A51 as you know, something as like a hash function that's suitable for rainbow tables. And we also have 204 data points or hashes over here that we can, you know, try to reverse back. And then even if we only get one of these, you know, we have really good chances of actually getting the real key. And this is really important because 64 bits is a huge amount of, you know, a huge key size for a rainbow table. So we decided that since we have all these data points, we only need 1/64th of the entire key space. But this is still a pretty huge number. 2 to the 58 is, I don't even know what that is. It's, yeah, billions of billions. Yeah, 288,000 billion, I guess. I don't know, or million, or yeah, it's a pretty big number. And it turns out that this key space is about 120,000 times larger than the largest landman rainbow table out there. So if you take the time it took them to create the largest landman rainbow table and did that times 120,000, then that's the type of space that we're talking about here. So it may possibly be the largest rainbow table ever created, but we'll find out. So we started looking at creating this, and it's like on one PC, we optimized it as much as we could, and we were only getting about like 500,000 A51s per second. So that meant that we would have to wait about 33,000 years to compute this, or grab 33,000 PCs and wait a year. So yeah, get some coffee for a year, yeah. And so we figured that was a little too long to wait. So do people here know what FPGAs are? I've given talks here before about FPGAs. So I work for a company that makes FPGA boards, and so we had a bunch of these FPGAs laying around. So the general idea is that normally with silicon, you create, you know, a processor for like, you know, running your applications or whatever, or you create like a graphics card processor, something that's geared towards, you know, some sort of purpose. So I created basically a processor that was intended on just, you know, creating these rainbow tables. And then you just upload it to the device and take over the world, right? So pretty simple. When we were generating the rainbow tables, we used 68 of our FPGAs, and that equated to about, what is that, 72 trillion A51s per second, and allowed us to do it in about 3 months with only 68 cards. And we're also building some new hardware that'll make things cheaper and speed it up a little bit. But this is actually a picture of the cluster and the card that we use. I've actually got one of them on my laptop, but we just used 68 of these just because we had them laying around. So the parameters that we used made it so we can do a cheap attack where if you happen to have 6 350 gig hard drives laying around and 1 FPGA or a botnet to do your calculations, which some people in the room may have, it takes you about 30 minutes to crack a conversation. And we're also working on a more optimal attack for commercial purposes that will take about 30 seconds. But the main problem with this attack is that it requires 2 terabytes of flash storage, or RAM storage, which is quite a bit. And we managed to get our hands on some, and but yeah, it's a kind of hard thing to find these days. So the other cool thing about this attack is that we can speed it up by just adding more FPGAs or more hard drives to the whole equation. And the reason why we had to go with flash drives is because of the random accesses per second. Normal hard drive, you can only get max like 400 or 500 random IOs per second, whereas on flash drives you can get like 10,000 off of each one. So then, assuming that you can actually reverse the output of A51 to the actual like internal state of A51, then you actually have to figure out what the key is. And so we built this method of reverse clocking the state back to the key. And essentially the main difficulty with this is that because we have this majority clocking sort of thing here, it's really difficult to clock it backwards. But there really isn't a huge amount of states when you analyze like all the possible clocking combinations. And so we basically do that, clock it back, solve some linear equations, and we have the key. And if you guys want a more detailed explanation, I can tell you later. But we're getting on average like 3 A51 internal states each time, and there's a couple different ways of determining if it's the correct one. You can just take the key, try to encrypt the same packet, and see if you get the same random stream out. Or you can just check for common states and stuff like that. But there's basically like this is fairly easy, and we just have it all scripted, so it's not that big of a deal reverse clocking it. So I don't know if you guys have seen this new paper that came out, but it's based on some really old attacks on A51 that date back to like 1998. There were a bunch of people that just started throwing out these attacks on essentially you brute force 2 of the registers, and then you kind of like solve the third one by just looking at the output of A51. And there's some optimizations that you can do that reduce the 2 to the 64 down to like 2 to the 48. And these guys implemented it on their hardware, on FPGAs, and it turns out that they can do it in about 14 hours with 120 FPGAs. And so to scale it to basically like our optimal attack, they need about 200,000 FPGAs to do the same thing as a rainbow table. So basically, like if you're trying to attack hash functions, rainbow tables are pretty awesome. So that's all I'm saying. And yeah, as far as other attacks, they're mostly infeasible. We looked at pretty much all of them. We've implemented some of them, and they just it doesn't seem like they would actually practically work for most people out there. So some details about this whole attack and how it applies to you. Remember that this only recovers the KC, which is the temporal key. And so it'll only recover the key for that one conversation. Some carriers also reuse the key for up to, I think, like 6 or 10 conversations after. So it's possible that you can reuse it, for a few more times before you have to crack it again. But it doesn't really give you like their master key. Like you have to keep on cracking. So it's it's within reach, but it's still kind of difficult to really implement something that'll like crack everyone's phone calls or do world domination sort of stuff. So in conclusion, there's a couple of things that you can maybe walk away from this talk with. GSM security should become more secure, or at least people should know that they shouldn't be talking about secure things over GSM. And there's lots of different products coming out for helping out with that. There's like the crypto phone. A lot of people are just moving to like encrypted VoIP and stuff like that. And I've been using this thing called CellCrypt, and that works pretty good. But anyway, just remember that somebody could possibly be listening over the line, and if anything, the operator could just be having taps like inside their data center. So please don't rely on the security of GSM. Also, just the whole tracking aspect with IMSIs being leaked. there's all sorts of implications for that, like targeted advertising on people, like you spot somebody doing something, you record their IMSI, and then every time they walk by, you like do targeted ads at them. You can see like where people are visiting, where people are going. I don't know. There's just lots of interesting areas that gray areas that people could exploit and just start spamming the real world. So it'll be really interesting to see how this stuff pans out. And then, of course, one of our things that we're worried about is unlawful interception, like unsavory characters out there like us, just sniffing to anybody's phone calls. So, I mean, it's possible in the future that this will become cheap enough that everybody here can do it, and hopefully new infrastructure will be in place to stop that sort of thing. And then, obviously, since we have a software radio that lets you listen to stuff, why can't we also make that transmit to the network? And that makes some other major implications. Just that, like, if we can just start writing code that starts sending out packets directly to the network, like you think that they've actually checked for buffer overflows in their switches? Is it possible to possibly route onto their internal networks and stuff like that? I mean, like, there's lots of interesting areas that people may start to look at once this becomes more within reach with actually playing with the network. And then with the amount of subscribers out there, it's just like a huge playground, and there's so many different possibilities of different attack vectors. So it's actually quite scary. And then also, yeah, just everything will become cheaper and easier. I mean, it's been out for, I think, 3 decades now, and our computing power is just increasing so much with Moore's Law that, like, in the next 5-10 years, anybody can do this sort of stuff. So it's good that 3G is slowly rolling out, and 3G should end up fixing this whole thing. But if there's backwards compatibility, then there's always the possibility of downgrading people back to GSM. So I'm not sure how I'm doing on time here. Looks like. Oh, okay. All right. A little early, but I can definitely take questions, and yeah, if you guys want some more detailed information, I can talk to you, like, out in the hallway and stuff. But just before I take questions, I wanted to do a couple shout-outs. TourCon 10 is going on in San Diego, end of September. We kind of release these dates at TourCon Seattle and I think maybe ShmooCon or something, but it's definitely this weekend. And we're also working on TourCamp next year. We're working on getting actually a abandoned nuclear power plant to camp out at. So we'll see if that works out. We're still talking with them. Otherwise, we're going to try and look at getting a missile silo or something like that. So look forward to that next spring. It should be pretty cool. But OK, so any questions, anybody? Oh, go ahead.
Yeah, what do you think is going to happen with the price of FPGA components with the big arms race between the graphics processing video card manufacturers? You think that kind of hardware will become suitable for this sort of graphic?
The question was like basically FPGAs versus GPUs and like how they can be used for cracking. I've started to see people using GPUs for doing crypto cracking. Like, I think that LCOMsoft actually just came out with plugins for their password cracking stuff that support GPUs, or at least they have a press release. I don't think they actually have software yet. But I know for the longest time the main problem was just doing like crypto stuff in floating point was a big problem, and so maybe they've managed to get around that, at least with certain cards. But yeah, it would definitely be interesting once, because GPUs are in like almost everybody's machine nowadays. It's hard to get a machine without a decent graphics card. So it would be really interesting to see how like people start writing distributed.net sort of stuff for this, and then suddenly you have like tons of computers on the internet that are available for doing that stuff. So yeah, it'd be really interesting to see what happens with that.
So the GPUs still aren't general purpose enough to do this natively?
Yeah, you're saying the GPUs aren't general purpose enough to do this natively. Well, I mean, it seems like if LCOMsoft is doing it, then there's probably some hack to do it, but I don't think it's really a mainstream sort of method because there aren't really a whole lot of things out there for doing it. There have been a lot of projects that sprouted up with using the what is it, the SPEs or SPUs on the cell processor, like for the PS3, and like there's there's web cracking support that I think HDM coded in for that. There's also, I think somebody did some WPA thing or something. So there's a couple different projects for doing that. But with that, they're mostly just using it, as like a few extra processors. So you get, decent speed up, but it's not really comparable to FPGAs with some algorithms. So any other questions? Go ahead. Oh, cool. Cool. Yeah. What was the name of the card again? A GS? I guess the GIA card has stuff for just solving math equations, so that would be interesting to look into for crypto. Go ahead.
Have the SIMs for GSM become more powerful as time has gone on?
The question was, have the SIMs become more powerful as time has gone on? Yeah, the SIM cards, now they have like Java virtual machines, they have tons of storage. There's, like Java applets basically like running on your SIM card. Yeah, there's definitely a lot of stuff that's been going on, and it's also constantly evolving. They're adding lots of new features to them and stuff like that. So it's almost kind of like just an extra computer inside your cell phone, right, that you can run code on and do stuff with. So it's really quite interesting. Yeah, thinking about, oh, well, something's wrong with my cell phone, so I'm going to take my SIM card and throw it in something else. It just keeps on following you, to new phones, and so it'd be an interesting attack vector if like viruses start coming out and like you can have it spread through the SIM cards and stuff, or I don't know. But oh, go ahead, Petty.
When you're talking about addressing the SIM card with the Java virtual machine, you said that it's possible for the service provider to take and push code into the JVM.
Yeah.
Now, using this project, would it also be possible to push code into the JVM if you were acting as a full-top?
Oh, yeah, the question was the operator can push code into the GVM, and so does that mean that you can, basically, right? I believe that the code that's sent to the SIM card is actually signed. And some people have said that it's actually signed with like some sort of a real signature, and some people have said that it's just based on like the source address that it comes from. And so there's kind of conflicting things, and we're still trying to figure that out, but that'll probably vary depending on the subscriber, how they implement what updates they want to receive. But basically, from what we know, all this stuff is verified on the phone before it uploads it to the SIM. And from the phone to the SIM, there isn't really any sort of authentication, as far as we know. That's our understanding of it so far. Go ahead.
So if you have physical access to the phone, would it be a simple matter to upload to the SIM card your hack, say, to prevent negotiation encryption or do some other nefarious tasks?
Yeah, the question was, could you then like upload your own stuff to the SIM if you had access to it? That's what we believe is possible. So yeah, like if you steal someone's SIM, you can.
Customs is checking your phone out at the airport.
Yeah, exactly. Yeah. So yeah, either way, you should watch out with for like who you give your SIM to. Another thing with your SIM is that because that A8 algorithm that I was talking about actually runs directly on your SIM, if somebody has recorded all of your conversations and they get access to your SIM, then they can run through and generate your session keys, like for whatever calls you've made in the past, and then decrypt them, if they have them logged. And so, there's lots of things that people can do once they have your SIM. It'd be really difficult for them to, compute all the possible keys for the future, but they can definitely get your past calls if they have them all logged. Go ahead. Oh, yeah. The question is, how does this stuff apply to BlackBerry and I guess like other IP-based sort of stuff like email and things like that? I believe that the cell phones use a totally different encryption algorithm for like GPRS and like Edge and stuff like that. So yeah, this stuff wouldn't apply to that. It would only apply to SMSs and calls. So as far as I know, the algorithms that they use for all the data stuff isn't really public, and we don't really know any information about it. So we may look into it in the future, but we don't really. Like for now, it seems like that stuff is secure until people figure it out. Any other questions? Oh, go ahead.
Well, one of them. You were talking earlier about that flag was supposed to be sent in ciphertext.
Mm-hmm.
When you were talking about the association channel. Remember the one I'm talking about? You can see.
Oh yeah, yeah, the IMSI. Yeah.
Now, if you were to take and clone the IMSI and then, make a hacked SIM or something else that you could take and load a key onto,
Mm-hmm.
would you be able to take and clone a GSM phone from that?
Oh, the question is if you get the IMSI, then can you kind of use that to clone the phone, right? Well, really what it comes down to is the key that's actually stored on your SIM. And so you'd have to extract the key from the SIM in order to actually be able to clone stuff like that. And yeah, you have to be able to generate the same session keys and like the same responses to authentication and stuff like that. So basically you have to crack the master key on the SIM. And with older versions of A8 or Comp 128, there's ways to do stuff like that. As far as the newer stuff, we don't really know what the new algorithm is. So if you have a newer SIM, then it'd be pretty difficult for somebody to clone that, at least in the moment. Well, yeah, I mean, like, they could always throw it under an electron microscope, drop down some probes, and like read off your key if they really wanted to. But just like dropping it into a reader and like, trying to get it that way is, we don't know of any way to do that with the new SIMs at the moment. So
they would have to add something extra to maybe change its functionality, but retrieving the master key would be very difficult.
Yeah. The question was, or comment, yeah. Yeah, and there's definitely ways to, like, intrusive ways of recovering it. Like, I don't know if you guys have seen Chris Tarnowski's talk, but he basically, like, decaps the actual dies and, like, drops down probes and reads. He can, like, read off the firmware off of the cards and also the KCs and KIs or whatever. So there's lots of different options for doing this stuff, but just like most people don't have the equipment to do stuff like that. So, I mean, it's kind of out of the question for most people. Go ahead.
I've seen these devices that where you read a SIM card like an SD card, it connects to a USB plug.
Mm-hmm.
Do those only read a subset of the data, or because it sounds like you're saying that these would let you read a full copy of a SIM card?
Well, the question was, you've seen like these things that are readers that kind of like SD cards that can like read stuff off your SIM. Are you talking about like ones that can back up your contact information and stuff like that, or?
I think that's how the one I saw was advertised.
Oh, okay. Yeah, those can't recover. Those can't recover your master key because there's no way with the protocol to actually read that back. It's it's like burned like into the SIM, and there's no way to read it back through software, at least as far as we know.
Is there like a hardware protected area, like on a hard drive, where you've got a segment that the manufacturer says you can't get there?
Yeah, exactly.
There's ways to get around that, and there's ways to get around SIM read by extending that area so that you're extending past the protected area, and now you can see the whole thing.
Yeah, exactly. Like a lot of smart cards and stuff like that either do like a lot of them do this thing where they like write into the region and then they blow a fuse like actually on the chip that makes it so it's impossible to read it back or anything like that in the future. And then so basically the only interface that you have to the master key is A8, which is you just feed it a random value, it spits back a response. Part of that is your KC, part of that is your response back to the authentication server. So aside from that, you don't really know anything about the key unless you, like look at the die directly. Oh, go ahead.
Provided there was a way to fix some of this data, which currently somebody is on the internet most likely getting solicitation content. You said that cell companies a lot of times hide like programs that shit on the SIM. Are there like emulators you know of where, let's say you had test code that you wanted to try to run, say you run on the SIM, and then emulators you can model it?
Yeah, the question was about the code running on the Sims, if there's like tools for developing stuff on them. We've managed to get our hands on like the Sim Toolkit stuff. I'm not sure how difficult it is for normal people to get it. It's kind of, I mean, like it's not exactly like a really hidden sort of feature thing, but there isn't really much talk about it. There aren't too many people developing for it, so it's there isn't a huge amount of information out there.
Smart card vendor has its own SDK for each type of chip. So if you're using, depends on the chipset you're using, if you're using 4 potential set or whatever.
Mm-hmm.
Depends on the smart card chipset.
Oh, okay. Yeah, you basically said that the
Back to manufacturer and try to get an SDK for them.
yeah, basically there's SDKs for the different types of card manufacturers, so so you can probably go to the card manufacturer and get the specific SDK for that. Any other questions? Okay, I guess that's it. I guess we got a freak show going on later, so I'll see y'all there.